Okay, good morning. So if you want to join Presenter, you can scan the QR code. And also maybe someone check everything's okay about the YouTube streaming. So later we will have the example for well-bound distribution. So, okay. So let me check it further. So today we will continue this example. The example here, we have the inverse transform. Before you do this, think about what is the inverse transform. We need to have CDF. So we need to have a CDF, for example, f of x. And then set it to u. And so that we want to solve x equal to something, and you will solve it. And finally, if we have the notation, it should be the inverse transform, right? And so that we can generate by generate u, step 1, and step 2, return x equal to this. So this is the inverse transform, right? We have the products for exponential. Am I right? Exponential. And right now, I ask you to have the exercise for this well-bound distribution. And the well-bound distribution, actually, you need to check. First of all, can you have this? PDF to CDF. All right. So you have a CDF here, CDF here. And then you need to solve this one so that you have the solution. Once you have the solution, we have this. Replace 1 minus u by u. And then you can have the formula. All right, so I leave all the annotated description here for your reference. But you need to check, first of all, this one. And then pass on this one. So step 1, step 2, and so that step 3. So all of you check the 3 steps. And finally, I will, of course, you can have a discussion. So right now, you can rearrange the seats and get closer to have the discussion. All right, so that you have 5 minutes to check this example. So check this for 5 minutes. Actually, you can have a discussion directly. So get closer. So rotate. We have 3 steps. You need to follow the 3 steps to check. Can you have the derivation for PDF? Oh, sorry, CDF. Then you reach second step. Second step asks you to find the solution x equal to something. And finally, you have the solution, so you can write the algorithm. So we have 3 steps here, right? So check it. Later, I will check all the goods. Everything is okay about the inverse transform. Santeri, Tobias, and Sue, Enzo, Yves, Matt, and let me think, Sang, and Ulis, Ben, Jerry, Jackie 4. Oh, Vincent, okay. I forgot these. So first of all, let me make sure. Step 1. Now, okay, then raise your hand. Step 1. Can you derive PDF? Oh, sorry, CDF. Step 1. No questions, right? Step 2. Solve this equation to have x. Okay, right? So finally, just follow this to have the solution. Generate U, and based on this formula, return this. Right? So we have step 1 to step 3. If you know all the steps, raise your hands. Step 1. No. If you know, step 1, okay, step 2, okay, step 3, okay, raise your hands. All right, so and Sean. Okay, right? So this one is the it's the inverse transform algorithm for this example. And the example here, it's important if you start from, for example, this one, and someone like you need to start from step 1 to step 3, unless that you are given the CDF directly. Or otherwise, you need to have the derivation from PDF to CDF. And then you solve the equation to get the solution x equal to something. All right, so this is the example. So inverse transform, it won't be any problem to you. And once we have this, we just want to have the observation. The current observation, we try to have the equal space here. So we have an equal length. With the equal length, then look at this. Wider range, smaller range. That says the common probability, but the interval here shorter, longer. So probability over length. So this is the density. Density high for this and density low for this. That's correct. So we just want to have the observation. Even we start from CDF, but based on this one, inverse transform, we can generate high probability around here and the low probability this one. So of course, we can have the PDF for sure. So this way, we just want to depth field. We base on CDF, but don't worry, we still can have the proper interpretation for PDF. So this one, we just want to depth field this. Actually, likewise, oh, okay, we can try again. If you don't feel we have a high density, we just let it have many lines, then you can find, okay, here you can feel high density, and here you have a low density. The current 2 pages just want to let you feel, even we start from CDF. Still, we can have the proper interpretation for the PDF, and that's it. All right, so this is the inverse transform. Up to now, any questions? Inverse transform. I think if you know the example to the previous example, then I think it's time for the inverse transform algorithm. So this is the first algorithm. And we want to have the generalization. General approaches to generating random variables if we still want to pass on the inverse transform. Think about this, we have a CDF, and also we have, here we have the probability mass function. So we can change to this one. The general approach, we can generate U. However, we want to find the smallest positive integer, I, such that we can test this. Okay, U lower than or equal to this one. The smallest index I, if we have the discrete case. Even we don't have the discrete case, we have the continuous case. Continuous case, actually, we can hold the equality. And so that know this problem. Yes, we just have the direct value x. But right now, we try to have the discrete cases. And discrete cases, we need to find index I. Oh, okay. The smallest index I can satisfy U lower than or equal to this. What it means? This one. All right, so if we have the given probability U here, it just asks you to find index actually 4. Here we have a 4. All right, so it just want to ask you 4 we have the for here. You actually should lower than or equal to this one. If we have a 4 greater than this, and 4 it is the smallest index, satisfy this. So it just asks you to return 4. So this is a similar idea. Oh, okay, we have a cut here. And actually, this is the corresponding value 4. All right, so for the discrete one, actually, we have the case 4. Actually, for 3, no. Right? So current point actually we know it's 4, but 4 belonging to the point here. So this one, not 4. In fact, this one is 4. So 4 greater than this is the smallest one. So we choose X4. And likewise, we pass on the graphical way to have the point, even it's discrete, rather than the continuous one. So we can have the interpretation. If you know the interpretation, of course, get back to this. Yes, it's true. Find the smallest one. If we want to ignore the current way to memorize, you just have a U here, and then try to have the testing, and the closest one is this one. All right, so it's this one. So that's why we find the smallest one, satisfy CDF greater than U a bit. And so that you return the smallest index 4. So it's X4. That's it. And think about this, if it's continuous, then we have the direct value, no problem. And so that this one can be put together. So can be put together here. The generalized one, inverse transform the generalized one for both continuous or discrete. We want to find X. X satisfies this equation, but X, it should be the smallest one. If it's continuous, smallest one is the direct one to that the equality hold. And if it's the discrete one, actually we have the smallest value satisfy this inequality. All right, so the general form should be this. F of X greater than or equal to U, and the smallest X serving as the value. And that value will be the value for the variable. Then just return this. So this is the generalized one. So we have the inverse transform, and previously we have the continuous case, and right now we have a discrete case. And put them together, so we have the general description satisfy this one. X greater than or equal to U, but the smallest X. That's it. And right now, we still pass on the current one to find the continuous one. Continuous one are actually the same. We just want to have a U, and we have the corresponding point. And right now, think about this. If we have the discrete uniform distribution, 1, 2, 3 to 100. So, based on the previous idea, it should be this one. Is it true? It says generate U. And if U lower than 0.01, so this one, 0.01, so which value you need to return? It's 1, right? And 0.02 is 2, 0.03 is 3. If we have the structure like this, fall within this, and then stop. Else you can continue. Else you can continue. So that you just try to find, oh, interval here, interval here, interval here. Try at maybe not try. Testing all possible interval. It's true, then return that value. It's true, then return that value. So In general, follow the previous discrete version. We should have the program like this, the code like this. However, we try to have the simplified version. How about this? Generate U, and we have U multiply 100. Multiply 100, then it's possible to be 0, right? So find flow plus 1, then this is the implementation for this one. Even you don't think it's the direct mapping, but feels like, oh, okay, based on the formula, we still have the range from 1 to 100. So it's true, we have the mapping. For example, think about this. 0.01, lower than 0.01, so it should be lower than 1. So we take 0. 0, then we have 1. Plus 1, then we have 1. So indeed, this one, it's the implementation. Right? So this is a discrete uniform. And think about this for 1 minute. I mean, finally, we have this. Even previously, we can have this one. But finally, we have this. And so that if you know this one, in the future, you just have the direct implementation using this one. So check it for 1 minute. So let me make sure about the final version. Uniform from 1 to 100. Okay, raise your hands. All right, thank you. So finally, just apply this formula directly. Unless you don't like it, you like the first one, it's okay, no problem. But the first one actually is the meaning, oh, okay, I have a U. Then just find the range. If we meet the specified range, then we return the corresponding value. And that's it. So up to now, first of all, you know how to generate exponential. And also you know how to generate well-bound distribution. Currently, you know how to generate discrete uniform. Am I right? So from chapter 1, you just know the generation for exponential. You don't know the reason, but right now you know the reason. Am I right? Currently, you have the reason to know how to generate the 3 types of random variables. Right? So let us continue. And here, even we have the way to generate the random variable using inverse transform, but we still have some possible situation to apply. Advantages. Actually, if we can apply, then we have some advantage here. I skip this one. But disadvantage, actually, sometimes can we have the solution? No. And sometimes, how about the case not wholly continuous one? Possibly you can have the mutual one, but it doesn't matter because we have the generalized version. So it's still okay if we can find the solution. That says if we can have it, no problem. We'll just do it. All right, so that's all. And check the however file to let me know. Currently, any questions? So you can see it, right? I mean, on pole everywhere. So that is half a 1 minute to finish this. Sorry. So not finished? So all finished, right? Let me check. So it should be okay. So let me continue. Why I want to check? Because currently it shows 0. So let me measure again. Not this pole. So let me check it again. So maybe something wrong, but let me check. So previously, you don't see it, or you see it. 刚才你看到是这个还是不是这个？ So previously, you answer for this question or not for this question? So wait a moment. If not this one, let me correct it. So maybe something wrong, we need to check these. So check it again. So this one correct, you see? I'm not sure what's wrong with the system. But this time I enforce it so you can see, and this time it's correct. So that's why I have a question, why it's 0? And once I check, okay, any question, but none of you let me know the question. So that's why it's a question. So this one correct. Previously, not this question. But why you don't want to let me know the wrong question? All right, so this one, not the previous one. So okay, that's all, and let me continue. And this one, attendance checking. So previously you finished this, right? I'm not sure. But this finished for all of you? If yes, that's okay. But some of you, if you still need to check it, you can check it. I'm not sure why it jumped to this one. The same one, the same question. Scan the QR code, then you see the same question. So maybe I enforce it. All right, if you want to continue, you can continue. If you finish this one, that's okay. If not finished, you can continue for 30 seconds. Sure, that's okay. If you answer already, that's okay. But you need to ensure you answered. So this one, finish. Okay, let me go to the next one. So right now we have this example. Group discussion 6. I select 3 problems from exercise, self-exercise number 2. Problem 1, problem 2, and problem 3. All right. And this time I let all of you to work on the 3 problems. If necessary, I can directly help for the presentation. So right now, I do not set the presenter. Just ask you to have the practice for all the problems. And for all of you, of course, you can try. Anyone, maybe for all of you can try. For example, Sandri, you can work on first problem, and Toby's work on the second, and Sue work on the third problem. And then you can discuss. Alright, so let me make sure for each group any possible solution to one of the problems for group 1, yes or no? Ready or not ready to anyone? Problem 1? Okay, maybe. Maybe. And the group 2? Yes, possible. Group 2? Ready for three of the, maybe one of the three problems? Yes or no? Problem 1, 2, 3? Any possible solution? 1, 2, 1. Sam, 1. And Sean, your group? 1, 2, 3, which one? 1 and 2. And the group 4? 1. 1. Only 1. And the group 5? It's 1, right? So that's okay. For problem 1. Problem 1, which one want to share your answer? If you feel okay, I should have the correct solution and I want to share. If yes, raise your hand from group 1 to 4 and 5. Which one? Sundry? Okay, so if Sundry, then you can share your answer on ugly bar, mentioning you are a presenter for problem 1. And so that TA can see directly. And of course, before 4 p.m., you need to upload answer to the 3 questions. At this time, you are the presenter. So you share your answer by mentioning you are the presenter for problem 1. Alright. And later, if I have the answer, I will ask you to have the presentation. And group 3, problem 2, from Sean, is okay? Sam, you need to share your answer. Before you answer, you mention I'm the presenter for problem 2. Alright, so right now, let me switch to this one. So, share the answer and so that I can ask you to have the presentation. So, Sandra, you first. But you need to mention you are the presenter and your answer here. Once finished, let me know. Perhaps I need to refresh it. Sean, for you. Sam, you are the presenter for problem 2. Mentioning this. So later we will share the possible solution from the 2 members. Of course, you can keep on working on your problems. Later, we will share the solution from 2 of the members. Talking about problem 1 and talking about problem 2. Actually, all the 3 problems concerning the maximum likelihood estimate, MLE. So MLE, we have MLE from chapter 6. Well, so we have the exercise that says you need to review if you want to finish the 3 problems. So summary, finished? You need to mention you are the presenter for problem 1. And likewise for Sean. Alright, Sean, you need to prepare your solution. And later we can check it and actually ask you to share. Okay, let me refresh it. Yeah. So that's why if you have any question, let me know. Once I refresh, then you will have the solutions here. All right, so this is the solution from Sandri and Jashan. So later for the presenter, speak loud and hold this. All right, so Sandri, you first. Come here to have your presentation. Go and share.
Yes, so well, if it's this is the mean, not the sample mean. I have the wrong sign there, but if it should be around the mean failures to get a success. So the chance of a success should be around 1 over x plus 1, or the mean plus 1. Since we offer expect the success after x failures plus 1 success, so total class is x plus 1. And since the probability that reflects the average of the sample mean should be since the probability that reflects that the sample mean is close to the real mean or the mathematical mean is the most likely value, so most likely should be p is equal to 1 over x plus 1, or the sample mean plus 1.
So, Sandri try to have the interpretation, right? So we can have the number of trials, 1 time over the number of trials. He tried to use this way, correct or not correct. You can take it for reference. So, Sandri, let me try how to have edit the post. Okay, that's it. So Sandri mentioned in presenter problem 1. That's correct. But for some, let me check. All right, so in fact, you need to mention something like this, but I do it for you. Presenter of a problem 2. And right now, come here and hold this. Speak louder. Hold that one.
So to find the enemy
Speak louder. No. Use it, no. Use that one, but speak louder, no problem. Not too close, yeah, okay. Speak louder.
So we will have the function of beta and gamma or
This is the likelihood function.
yeah, the likelihood function of average. So because so we will calculate the log likelihood of this function.
Okay.
And for this.
So right now you have 2 parameters, right?
Yeah, right. So
Beta and the gamma.
Yeah. So I will optimize for gamma first, beta first. So we will
Differentiation.
yeah. Equal 0, so we will have
Okay, so this is beta.
yeah.
And then how about gamma?
Yeah, gamma we will calculate this gate. So
Likewise, you have the differentiation, right?
yeah.
Set it to 0. Can you find the solution?
No, set for 0 because we see that in this function when we have the maximum of gamma equal mean of is equal to began. When we set this is
So that sense for gamma, you have the special treatment.
Yeah.
Finally, you think the solution should be the first observation, right?
yeah
If we have the older observation, the smallest one.
yeah
But maybe a bit more detailed reason why you
Yeah.
choose this one.
yeah I think I do.
Okay. So finally, first one and second one, put them together, you have the solution for this problem MLE.
Yeah.
Okay.
So we will rewrite this again for gamma and vector gamma.
Alright. Okay. That's it. Thank you. So no worry. This is microphone, but not too close. Something like, oh, okay, here. So that's okay. But speak louder. And in fact, I open this as well. But I rely on this rather than this one. So someone like this one, speak louder. No, not too close. It is okay. You still can hear you if you speak louder. So this is the presentation from Saunders and the presentation from Sean for the two questions. Actually, for the first question, Saunders tried to have the interpretation correct or not. I'm not sure, but later we can check the problem. And for the second problem, is the standard procedure. We base on the MLE formula to have a likelihood function. And to have the differentiation, sometimes it is not easier. So we have the log likelihood function. Then, if we want to find the solution, we need to perform differentiation. But sometimes, differentiation set it to 0. We won't have the solution, but still try to find where we can possibly have the maximum value. For Sean, maybe some reason he thought x1 should satisfy maximize the function. So he chose the smallest observation, right? But reason should be clear. All right, so this is the reference discussion from Saunders and Sean. All right, so double check the problem again. Problem 2 actually asks you to have the MLE, so it's correct. Procedure from Sean is correct. So procedure from Sean is correct. And likewise, you can apply this procedure to problem 3. Problem 2 procedure can be applicable to problem 3. Alright, but you need to check it further. And problem 1, that's correct as well, because it doesn't ask you to have MLE directly. No, it just wants to ask you to explain. So someone like reason from summary perhaps is correct for your reference. Alright, so we have 2 solutions here for your reference. Of course, you can use them for the further solution for you, but it doesn't mean use them directly. You still need to prepare your solution. And that's on problem 1 and 2. So finally, you have the solution to problem 3 as well. And we don't have enough time, so usually we set it to 4 p.m. And this you need to upload your answer to ideally before 4 p.m. Is it okay? If that's okay, that is time rest, and then that's close the discussion for good discussion.